Okay, here's another example problem. Now, you may want to take notes on this because this is not an example that's in the book. It's an example that's interesting to me. I actually dug next to my house about a 9-foot trench and laid a bunch of pipe to go out. The area of my house, or area of my property, has a small ravine on it because they built it up with a dam to build a pond. So that on the opposite side of the pond is a ravine, essentially. It's a big pain to mow, and someday I want to fill it in. But I thought before I filled it in, it would be nice to go ahead and lay the pipe to eventually have a geothermal system. And so I was thinking about it, and I thought, well, now wait a second. Even though I buried this pipe about 8 feet beneath the ground, what's going to happen to it? How would it lose heat? Because I didn't bother insulating it. I assumed the ground around would be insulation, since I want to transfer heat with the ground anyway. But let's just say that I'm concerned about heat transfer from this pipe in the ground that runs out to the field, because eventually I want to run this out and do a YouTube, not a YouTube video, but a YouTube heat exchanger in the ground, which are geothermal bored holes, about 300 feet in the ground or so. So that part I'm not worried about. It's the piping going from the house to these essentially not wells, but they're live wells. Anyway, that's the part I was concerned about, and I wanted to do some calculations on it. So this is what I did. I assumed that I had about 100 feet or so of piping. And I'm just looking at one particular pipe. The thermal conductivity of the dirt, the best number I could come up with was about 0.96 BTUs per hour per foot per degree Fahrenheit. And I think that that was for wet dirt, which is more thermally conductive than dry dirt. I don't remember where I got the number, but it was reasonable. I may have looked it up in the back of our book. I don't recall right now. And I assumed what would happen if the temperature of the air were at 20 degrees Fahrenheit. Okay, so this is at the surface of the ground. And 8 feet is pretty deep. That's not too bad. But I was curious what would happen anyway, so I worked up this little problem. So 8 feet. The diameter of the tube, it's nominally 1 inch polyethylene, but I measured it and it's about 1 1/4 inches in diameter. And I assumed that the temperature of the pipe would be about 58 degrees Fahrenheit. Now, if water's flowing through, say, in this direction, and the temperature's at 58 degrees Fahrenheit, and it's losing heat, then obviously the temperature is going to go down. But it's not going to go down a lot. So I'm just taking sort of an average temperature of 58 degrees. Okay, because the bulk heat transfer that I'm interested in is from here up to the surface. Okay, so this is the perfect case for a shape problem. So which particular case would this be? What do you think? We're going to use the same equation, Q dot equals SK, T2 less T1, or T1 less T2, I guess, in this case.
This would be the first situation buried in a semi-infinite medium.
That's right, first case. It's a cylinder buried in a semi-infinite. What does it mean by semi-infinite medium? What that means is that the dirt, as far as we're concerned, goes forever in this direction. Does that make sense? You know, obviously, if you kept going this direction, eventually you'd reach Middle Earth, right? And then China. If you're in the cartoons, you just go through in about half a second, right? You can talk to them. But anyway.
We'd actually end up on the ocean, just FYI, from where we're at.
Oh, yeah, you're right. We'd end up in the ocean. That would be a problem. We'd spring a leak in the ground, right? Yeah. Cartoon physics are quite entertaining. Okay, so the shape factor. Any questions so far? I see discussions. Okay. Shape factor would be 2 pi L over the natural logarithm. That's an easier button to find in your calculator than the last one, isn't it? Of 4z over d. Bless you. Now we have to be a little bit careful because d and z have different units, right? In fact, d has units of inches and z has units of feet. And so we have to take that into account. So 2 pi times 100 feet, the argument in the natural logarithm has to be dimensionless. So for z is 8 feet, okay? Then I have to divide by d, which is 1.25 inches, so I'll have to convert it to 1 foot per 12 inches, and that part goes away, and life is a lot better because the feet will go away as well, and I'll have an argument in the natural logarithm that is dimensionless. So when you plug all this in your calculator, you find that the shape factor is 109.7. 109.7 what? What are the units? Feet, right? That's all that's left. natural logarithm returns something that's dimensionless, right? You give it something dimensionless, it gives you back something dimensionless. So it's just feet. So 109.7 feet is the shape factor, which is actually kind of interesting because that's reasonably close to 100 feet. And obviously I just plucked this out of the air, right, for 100 foot of pipe. What's the heat transfer rate? So it's interesting the shape factor essentially comes out to about 100 feet. But anyway, plugging all this in, 100 feet multiplied by the thermal conductivity, 0.96 BTUs per hour, per foot, per degree Fahrenheit, multiplied by then T1, 58 degrees, less T2, 20 degrees Fahrenheit. Degrees Fahrenheit go away, feet go away, we'll get BTUs per hour. And the number of BTUs per hour is about 4,002 BTUs per hour. For whatever reason, I was very lucky when I made this up and all the numbers came out to numbers that looked like they were just made up. Okay, it's about 4,000. What do you know? You must have made it that way. Actually, that is it. So 4,002 or so BTUs per hour. Now, here's an interesting discussion to have. Anytime you're dealing with a geothermal system or a heat pump or an air conditioner, you usually rate the capacity of these things in something called tons. Okay, now a ton, where did the concept of a ton of refrigeration capacity come from? I mean, I've got a ton of refrigeration capacity at my house. Actually, that's not a whole lot of refrigeration capacity. Most houses have 2-3 tons, something like that, of refrigeration capacity depending on their size. Well, what does that mean? Well, if you take water at 32 degrees Fahrenheit, okay, and you've got a ton of it, and you extract thermal energy from it, you have to extract thermal energy from it at a rate of 12,000 BTUs per hour for 24 hours in order to turn it from liquid into solid. So it'll take 24 hours to turn literally 1 ton of water from liquid 32 degrees to solid 32 degrees if you extract 12,000 BTUs per hour from it. Make sense? So what is this? Well, this is about 1/3 ton of capacity, which to me is actually very interesting because I calculated the rate that I actually needed. If I were to turn on a heat pump and run it continuously in my home just to maintain the temperature average throughout the winter, I need about 1 ton of heating capacity. I need about 12,000 BTUs per hour, just on constantly. Obviously, I wouldn't want it to run constantly, and so I actually intend to put in about a 5-ton unit or so, maybe 8, because I plan to add on to my house. But anyway, it's really interesting to me that one of these pipes would actually lose 1/3 ton of capacity. That's really interesting, because what that means is that if I go out 100 feet from my house and I put in a geothermal well with a 200-foot, depth, I've got to oversize it a little bit because for each well, each pipe going out to that well, I'm going to lose this much if the temperature's at 58 degrees. Now that's sort of a worst case scenario because really the low ground temperature in this area is more like 55 to 57 degrees. And what's kind of interesting is with the geothermal system, as you run it during the winter, since you're sucking heat out of the ground surrounding it gets colder. In the summertime, since you're dumping heat into the ground surrounding these wells gets hotter. So basically the ground around all this piping gets hotter. But for a back of the envelope calculation, I was really surprised that at an 8-foot depth, I could lose 1/3 ton per 100 foot of pipe. So it's just interesting. Questions, comments?
Did you mean to write 100 feet in your equation for Q?
That's the 109.
The 109?
I did mean to write 109, thank you. Yeah, I should have been 109, because that's the shape factor, whatever it was. The number should still come out, I just copied down the wrong number. Good question, anything else? All right.